What I wanted to introduce you to today was something a little bit different. Today I wanted to talk to you about what's called organic chemistry. You see, organic chemistry is an entire field of chemistry, and it's all based around the study of one atom and the compounds that it can create. And that atom is carbon. And the reason that we have an entire field devoted to the study of carbon is because carbon can do some things that nothing else can do. Carbon is able to make compounds unlike anything else that we've discovered. And it all has to do, as you probably guessed, with the structure. In order to understand this structure, we have to go back a little bit to understanding orbitals. So we're going to take a look under the camera and we're going to talk about carbon. So if we're talking about carbon, here's what I want us to consider. Is the Lewis dot structure for carbon shows that it has 4 unpaired electrons. Now this is extremely important because carbon is able to form 4 bonds. And carbon will always form 4 bonds. That's what it does. Almost every single compound that I can think of, except for a few oddballs here and there, has 4 bonds to every carbon atom. But remember when I talked about orbitals and I mentioned that we can learn a lot about a substance and the way that it works from its orbitals? Well, I'm going to throw a little twist in here. When we take a look at carbon, let's take a look at carbon's electron or orbital notation. And so to draw the orbital notation for carbon, we want to consider how many electrons it has. It has 6 electrons, and based off of everything that I've taught you, we should come out to have 4 valence electrons, and those 4 valence electrons should all be unpaired. And so let's take a look. We start with our lowest energy orbital, the 1s. It's full. We move on to the 2s. It would be full, which moves us to the 2p. P's have our 3 shapes. We need 6 electrons in total, and I've used 4, so I get 2 unpaired electrons. So how does this work? Based on what I've drawn for my orbital notation, carbon should look like this. Right? It should have 1 pair of electrons and 2 unpaired electrons. But we know this isn't the case. We know carbon is not like that in any way. In fact, we know it has 4 unpaired electrons because it's able to form 4 bonds. So we need to figure out what's going on here. If we want to be able to understand the chemistry of carbon and how it's able to do these things, we need to understand the atom of carbon and be able to apply what we know about it. In order to understand what's going on, we need to actually think about the orbitals. So remember when I introduced you to the ideas of orbitals and I said you'd have your nucleus in the center. 1 means closest to the nucleus and S means sphere. So you'd have your 1 sphere closest to the nucleus. And then the 2 means we're a second distance from the nucleus. And S means a sphere. And you also, at the same distance from the nucleus, have 3 p orbitals. And remember, those are those dumbbell shapes. So you have 1 on the x-axis, 1 on the y-axis, and 1 is on the z-axis, popping in and out of my board here. Now this is what I showed you, but there's an inherent problem in this. You see, the 2s and the 2p are actually trying to occupy the same space. And electrons are matter, like physical matter that have mass and have volume, and 2 pieces of matter cannot occupy the same space at the same time. So carbon is able to do something a little bit different. In fact, most bonding ends up kind of working this way, where carbon creates what is called a hybrid orbital. And that's exactly what it sounds like. It is literally a mashup of 2 different kinds of orbitals. You see, a hybrid orbital is a set of orbitals that have combined together into a new shape, and they do this because they're actually trying to occupy the same physical space. And so in carbon, what we see is we used to have this 1s, 2s, 2p situation. But what carbon does is actually take the s and the p orbitals and combine them together. So remember, an s orbital is a sphere, and a p orbital is a dumbbell shape. When you combine them together, you end up getting something that I think actually looks a lot like a balloon. This is an S and P combining together to make an Sp hybrid orbital. Now, there are actually different kinds of Sp3 hybrid orbitals, but in this video, I'm going to focus on the main one that we're going to be dealing with in organic chemistry for the most part, and that is what's called an Sp3 hybrid. So when carbon takes its s orbitals and its p orbitals and combines them together, what it ends up creating is 4 sp3 orbitals. And these are at the second energy level. And so we actually get 4 different shapes. The reason we call it sp3 is because it's made of one s orbital. So in other words, it's made of one sphere and it's combined with 3 p orbitals, or those dumbbell shapes. And that ends up producing 4 different orbitals that look like this. Because there are 4 electrons, and by combining these together, they are now at exactly the same energy level. So they now follow Hund's rule. We have to put 1 electron in each of these orbitals before we can pair any up. This is what ends up creating those 4 unpaired electrons. When carbon combines those s and p orbitals into sp3 hybrid orbitals, you end up getting 4 electrons that are unpaired. And that is the key to what carbon is able to do that other elements really aren't able to do quite as well. So the combination of the s and p hybrid orbitals to make those 4 orbitals, each with 1 unpaired electron, ends up combining that sphere and that dumbbell shape, and you get something that kind of looks a little bit like this. You get like this little nubby end, and then you get this larger portion. And because each of the orbitals ends up looking like this, you actually end up with 4 of them. Now remember, these orbitals were trying to occupy the same space, and that space was around the nucleus. So what's going to happen now is you're going to have your nucleus, and each of those balloon shapes is now going to move in a way that they can essentially get out of the other orbital's way. Now, these 4 sp orbitals that have been made have to be able to fit around the nucleus, but without overlapping each other. And the way that they do that should hopefully look a little bit familiar. So I put this together. This is my 4 sp orbitals. And the way that they would combine is all of those small parts would just be kind of overlapping, well, not overlapping, but combined in the center. And this is ultimately, if you were able to do some measurements and take some calculations, you would get something that kind of looks like a tetrahedron. You see, that is ultimately what happens. When the sp3 hybrid orbitals form, you end up getting 109.5 degree angles, and you end up getting a tetrahedral shape that surrounds the carbon. And that is ultimately what's so important here, is that the carbon is able to form that tetrahedral shape, and it's able to form 4 bonds with pretty much all of the other things that we're going to end up seeing in this unit. And it's going to do that all because of hybridization. So hopefully this gives you a better sense of what we're getting into and what organic chemistry is going to be about. And kind of the big takeaway here is that carbon always needs 4 bonds, no matter what. So thanks for watching, and I'll see you next time.